All right, so what I want to do now is discuss how to integrate very general non-negative functions um, in a way that'll end up extending how we've integrated bounded measurable functions on a set of finite measures. Okay, so to do that, we need two simple definitions. First, if I have a measurable function defined on some measurable set E, its real value, we say that f has finite support if the measure of all x and E where f is not equal to 0 is finite. So on E, f is 0 except possibly on a set of finite measures. Okay. And for such a function that's bounded and measurable, we can define its Lebesgue integral in some sense, the obvious way. So first of all, well, the double dots, if I haven't mentioned this before, these two dots with the equal sign means we're defining something. So this is not a theorem. This is not something we're proving. This is a definition. And this makes sense because E0 has finite measure. F is bounded, and it's measurable. So we've defined this integral in previous videos. In particular, f is Lebesgue measurable on E0 because it's bounded and measurable, and E0 is finite measure. Second of all, this makes sense intuitively because outside of E0, f is 0, so outside of E0, E take away E0 should have no contribution to the integral. So it makes sense to define this integral as the integral over E0 of f. Okay. So with this definition in hand, we can define the Lebesgue integral of a non-general, non-negative function as the supremum of all these integrals where we're integrating all these h's, where h is bounded, measurable, it's finite support, and h is less than or equal to f on E. Okay. So I should mention that really you don't need f is measurable to define this integral because, well, even if f is not measurable, this integral here, all these integrals over h, for all these h's, it's well defined. The only thing is you really can't prove anything about this Lebesgue integral if f is not measurable, as we will see momentarily. So it's pretty pointless to deal with this definition when f is not measurable. Second of all, this set here, without the supremum, it's a set of real numbers. Each one of these integrals is well defined as a real number. And this set here is, it's not empty. If f is non-negative, then h equals 0 on E certainly fits the bill. H equals 0 is bounded, measurable, has finite support, and 0 is less than or equal to f if f is non-negative. Okay, so that also says as a supremum, this integral here is bigger or equal to 0, as long as f is non-negative, which should be true, obviously. And also, there's no reason why this set of real numbers, of non-negative real numbers, is necessarily bounded above. And in fact, I'll do an example in a second of where it's not, and therefore this Lebesgue integral, by definition, the supremum of a set that's not bounded above is by definition infinite. And that's nothing subtle, nothing strange. Inherently built into this definition is integrating unbounded functions, or maybe not even just integrating unbounded functions, just integrating bounded functions over E, where E does not have finite measure. Either way, it's not a big deal if this set is not bounded above, in which case the supremum is infinite. Okay, so I did mention this extends the definition we previously had for a Lebesgue integral when f is non-negative. And it does, in fact, extend that definition we had before. In particular, in general, if f is non-negative and measurable, then this definition here coincides with the supremum of all these integrals where phi is simple, has finite support on E, and phi is less than or equal to f on E. So in particular, when E has finite measure, it's superfluous to say phi is a step function on E has finite support, because away from E, phi is 0 if phi is a step function on E. And if E has finite measure, then phi trivially has finite support. So in other words, when E has finite measure, this set here is literally this set right here. And this is what we use to define the Lebesgue lower integral for a function that has bounded, a bounded function that is measurable and it's defined on a set of finite measure. Okay? So in particular, in the case, in the case when when E has finite measure and when f is bounded, this definition here, which equals this supremum, that's for homework, coincides with exactly the previous definition. So this is really an extension of the work we've done, of definitions we've dealt with before. And of course, I'm there, implicitly assuming, as we proved, that a bounded function that's measurable on a set of a set of finite measure is Lebesgue integrable. We proved that functions that are measurable and bounded on a set of finite measure is Lebesgue integrable. Okay, so you might be wondering, is anything like this true for simple functions larger than f, kind of like the definition of the upper Lebesgue integral? And the answer is no, not in general. And in particular, if f is non-negative and unbounded, then there does not exist a simple function larger than f on E. This is basically trivial. It's by definition. Okay? If f is non-negative and psi is bigger or equal to f, and f is unbounded on E, then psi has to be unbounded on E. There does not exist unbounded simple functions. By definition, a simple function takes on finitely many real numbers on E. Okay? Any finite set of real numbers is bounded. Okay? So in particular, what this is saying is that if f is unbounded, then this set here, f is unbounded, non-negative, then this set here is empty. Just the set of all these simple functions larger than f on E, it's empty. So how do you integrate something that doesn't even exist? So this really has no meaning if f is unbounded. Right? And we really do want to consider unbounded functions. You spend time in Calc 2 doing improper integrals. So you integrated something like 0 to 1. From 0 to 1, you integrated x to the minus 1/2, which is 2. Integral from 0 to 1 of x to the minus 1/2 is 2. So for this reason, it's not necessary, and we're not going to ever need to kind of put conditions on f so that we can get inequality of this Lebesgue integral in terms of these larger simple functions. It's just not necessary. It's not necessary. You can't do anything with unbounded functions, so there's no point. And I should mention that this is not easy by definition. This is not that easy to prove. On the other hand, it'll actually turn out to be very easy to prove after we've proven some really heavy-duty theorems in the next video. Once you basically have, so to speak, the proper artillery to attack this problem with, it's pretty easy. All right, so let me do an example where the Lebesgue integral is infinite. So in particular, let's say f of x is this characteristic function from 0 to infinity. All right, certainly measurable, non-negative. Okay, so let's prove that the integral of this function on the set 0 to infinity is infinity. So how do we do that? And how do we deal with the Lebesgue integral often in general, especially when we want to estimate it? Well, we're going to pick a convenient h, and then the supremum is going to be bigger or equal to that integral, the integral of that convenient h. So in particular, the Lebesgue integral will be bigger or equal to the integral of this convenient h. So the convenient h will be, that we'll pick for this problem, is the characteristic function from 0 to n. Certainly that's less than or equal to f of x on 0 to infinity. It's bounded, measurable, have finite support. If you're away from 0 to n, it's 0. So the Lebesgue integral of f is the supremum of all these integrals over all these h's. So it's certainly bigger or equal to the integral over this one particular h. And we're just integrating a characteristic function from 0 to infinity. It's just, the measure of 0 to n, which is n. And so this Lebesgue integral is bigger or equal to n for every natural number n. There is no non-negative number, real number, bigger or equal to n for every natural number n. So that forces, by definition, Lebesgue integral to be plus infinity. So again, this is nothing subtle. This is, you just have to embrace this. This is something that's built into the definition. So what I want to next prove is a foundational result that you might have actually seen in a probability class, and you might have even proved the weak law of large numbers using this result, which is weak law of large numbers really is one of the cornerstones of real probability theory. Okay, so what is this? Well, if f is non-negative and measurable on E, and if lambda is bigger than 0, then the size of this set here is less than or equal to 1 over lambda times this integral. Okay, so how do we prove this? The proof strategy is exactly the same thing as the strategy here. We're going to pick convenient h, okay? And the Lebesgue integral, we're going to pick convenient h, that's bounded, measurable, has finite support, non-negative, and less than or equal to f on E. So the Lebesgue integral is going to be bigger or equal to the integral of this convenient h. And roughly speaking, that's going to give us, when we integrate this convenient h, roughly speaking, we're going to get lambda times this measure. Not exactly, but roughly. So what's this convenient h? Well, we need h, so you might think just let h be the characteristic function of E lambda. It's not a bad guess. But it's not, doesn't have finite support, so we need to truncate E lambda to minus n to n, and then define a characteristic function times lambda to get a hn that is that has finite support. So I think I said you might have thought to use a characteristic function of E lambda. I meant lambda times the characteristic function of E lambda. Okay, so let's check that hn is less than or equal to f on E. There's two cases. If x is an E lambda n, then hn of x, definition of this characteristic function, is lambda. But on E lambda, and particularly on E lambda n, lambda is less than or equal to f of x. So hn of x equals lambda is less than or equal to f of x. Now, if x is an E take away E lambda n, this characteristic function is 0, so hn of x is 0. I don't care what f of x is. If it's non-negative, then 0 is less than or equal to f of x. So we've proven that hn of x is less than or equal to f of x on E. So we're going to integrate hn of x. Nothing subtle there. It's just this characteristic function times lambda. So it's lambda, the measure of E and lambda. Again, this Lebesgue integral is the supremum of all these integrals over all these h's, where h is bounded, finite support, measurable, non-negative, and less than or equal to f on E. So the supremum is bigger or equal to this specific integral over the specific hn. So we almost get what we want by dividing by 1 over lambda. Instead, we get this truncated set is less than or equal to the right-hand side that we want. Well, thanks to the exam 2 first problem, we can use continuity of measures. So remember that problem on exam 2, the first problem, states that for any measurable set, the measure is going to be the limit of the measure of that set intersect minus n to n as n goes to infinity. We're just applying this to the specific measurable set E lambda. I should mention E lambda is clearly measurable because f is measurable. So this set here is measurable. Okay. So by continuity of measure, the measure that we want is this limit, but for each n, we have this upper bound. So certainly the limit has to satisfy the same upper bound. Okay. So this proof is rather typical of how you essentially often use definition of the Lebesgue integral. Right? And I should also mention that books don't often do this. So often books simply define the Lebesgue measure as this supremum. One of the advantages of defining it as the supremum of this possibly larger set is that when we prove Fatou's lemma, the proof is actually going to be easier than it usually is. So there is some use to, even though these two coincide, there is some use to actually using this more flexible definition than just restricting ourselves to simple functions that are less than or equal to f. Okay, so let's use this Chebyshev's inequality to prove the following fact, that f equals 0 almost everywhere on E if f is measurable non-negative, if and only if this integral is 0. So there's two reasons why this is not trivial. It's not a hard result, but it's not trivial. First of all, it's not trivial by definition, or it's not 100% immediate by definition that if you take like the integral of 0 over the real line that you're going to get 0. That's got to be proved. It's not hard, but you got to prove it. In particular, intuitively, you might think, well, maybe that's like 0 times infinity. So we still have to prove it. Second of all, it's not clear immediately why this equals 0 implies f equals 0 almost everywhere. You might think, well, can't I just plug in 0 into Chebyshev's inequality? If f is non-negative, well, first of all, if f is non-negative, first of all, lambda equals 0 means nothing for Chebyshev's inequality because, this is going to be just infinity. And even if this integral is 0, we're not going anywhere near 0 times infinity. Remember from Calc 2 that could take on any value whatsoever. We're not going near 0 times infinity in this course. Okay. Sometimes books do define it as 0, but I don't want to do that. Right? So yeah, second of all, this is for bigger or equal to, so even if you could plug in 0, that's not useful. We want that the set of all x and E where f of x is bigger than 0 is 0 if f is non-negative and this integral is 0. Certainly, the set where f is not 0 if f is non-negative is the set where f is bigger than 0. All right, so let's do the easy part. And that is, if f equals 0 almost everywhere, then this integral is 0. Again, it's not subtle, but we still have to prove it. So let's say h is less than or equal to f, non-negative, and h is bounded, measurable, finite support on E. Well, if f is 0 almost everywhere and h is sandwiched between 0 and f, then h has to be 0 almost everywhere. So it's an easy homework that the integral of h over E is 0. And again, we know how to do this integral. We're not using, it's not, it's just this integral, this definition right here, since h has finite support. And this integral here over E0 is just the upper-lower common definition. And it really is very easy. Okay, so what does that tell us? Well, the Lebesgue integral, again, is the supremum of all these integrals over all these h's. This was just an arbitrary such h. So that this set here, defining the Lebesgue integral for a non-negative measurable function, the set here is literally 0. All these integrals are 0. So this is the set containing, this is a singleton. Okay? So the supremum of the singleton containing 0 is obviously 0. Okay, so for the converse, even though we can't plug in lambda equals 0 for Chebyshev's inequality, we're going to do the next best thing, which is define convenient sets that we can use Chebyshev's theorem on, and relate the set we want to measure to those sets. In particular, let's say E prime is a set of all x and E, where f of x is positive. Of course, that's the same thing as a set of all x, where f of x is not equal to 0, since f is non-negative. So it's pretty trivial that E prime is this union, because if x is in one of these ENs, it's obviously f of x is bigger or equal to 1 over n for some natural number n, which is bigger than 0. So x is in E prime. If x is in E prime, f of x is bigger than 0. So it's bigger than 1 over n for large enough n. So it's in one of these ENs. It's in all of these ENs for large enough n, but anyway. So clearly these sets are ascending. So we can use continuity of measure. And we apply Chebyshev's theorem to En. Here lambda is 1 over n, so it's 1 over n, which is n. Okay, so now we're in this situation where there's nothing wishy-washy about this. Any n, no matter how large it is, times 0 is 0. N could be a million, gazillion, trillion raised to the million. Still multiply it by 0, it's 0. So this is the 0 sequence, so the limit's 0. So again, using Chebyshev's theorem on each of these ENs and using continuity of measure allows us to avoid some infinity times 0 situation. And again, there's nothing wishy-washy about this. This is some integer times 0, which is 0, even though that integer may be large. All right, so let's now prove the linearity of Lebesgue integral. Okay. So a large part of this is just like linearity for the Lebesgue integral when f is bounded, measurable, and f is defined on a set of finite measure. Okay. In particular, the proof that you can pull out constants is basically the same, so that's for homework. And also, half of additivity for the Lebesgue integral is also basically the same. Actually, this for the Lebesgue integral for bounded functions on a set of finite measure, that was also for homework. So, so yeah, basically, you're going to prove this twice for homework. That's okay. All right. Actually, I think it was the other direction that was for homework. It doesn't matter. Okay, so let's prove the other direction here. And that's a little tricky. It's a little tricky. It's a little tricky because for the old definition of the Lebesgue integral for functions that are bounded on a set of finite measure, we have both the upper and lower Lebesgue integral to play with. And you know, the converse to this would be a lot easier if we could utilize infimums. We can't. So we just have to be clever with using the definition of the Lebesgue integral as a supremum. Particularly, let's say H tilde is bounded, measurable, finite support, and H tilde is non-negative, but less than or equal to f plus g on e. So I claim that I have the following, and I also claim that if this is true, this inequality, then I'm basically done. Well, there's two cases. The first case is one of these integrals is positive infinity. Well, if one of these are positive infinity, then the converse to this here is trivial. You have positive infinity is less than or equal to well, yeah, you have positive infinity. You have positive infinity. If one of these is positive infinity, then the converse, the other direction for this inequality is trivial because you have infinity is bigger or equal to something non-negative that might be infinity. So let's assume that these are both actual real numbers. So what this is saying is that this real number is an upper bound for all of these integrals, but the supremum, the Lebesgue integral rather of f plus g, is the supremum of all these integrals. The supremum is the least upper bound, so this particular upper bound is bigger or equal to the least upper bound. Okay. And that's exactly what we wanted. It's the converse to this inequality here. So we have to prove the main claim. And the strategy is going to be just like the strategy before. We're going to cook up two useful functions that we can essentially plug into the definition of the Lebesgue integral, one for f, one to g, so that we can estimate these two Lebesgue integrals, particularly get an upper bound, a lower bound for these two integrals. Okay. And how to do that is not that trivial. It's not hard, but it's a little subtle on how to pick your functions. So I claim that h and k defined as here fit the bill. They do exactly what we want. So first, let's check that these are bounded, measurable, with finite support, and that h is less than or equal to f and k is less than or equal to g. Well, h is trivially less than or equal to f, because this is the minimum of f and h tilde. Okay, so yeah, first of all, h as a minimum is also less than or equal to h tilde of x on e. So it's non-negative because both f and h tilde are non-negative. It's bounded because h tilde is bounded. It's measurable because it's the minimum of two measurable functions. And it has finite support because when h tilde is 0, h is 0. Okay, and also, well, basically saying the same thing, h of x is less than or equal to h tilde of x. So that means k of x is bigger or equal to 0. And it's less than or equal to h tilde of x because k of x is h tilde of x minus something non-negative. Okay, so also k of x is bounded because h tilde is bounded. It's measurable as the difference between two measurable functions, neither of which ever spits out plus infinity. And has finite support because, well, when h tilde is 0, k is 0. Okay. So as I mentioned, it's absolutely trivial that h is less than or equal to f on e. Just again, because h is the minimum of f h tilde. So I claim that k of x is less than or equal to g of x on e. And we just have to look at two cases. So the first case is f of x is less than or equal to h tilde of x. Okay. So in this case, when f of x is less than or equal to h tilde of x, h of x is going to be f of x, because f of x is less than or equal to h tilde of x. So the minimum is f of x. So h of x equals f of x. So k of x definition is h tilde minus h. H is f. So k is h minus f. But h tilde, remember, we picked it from the very beginning to be less than or equal to f plus g on e. Remember, h tilde is kind of our h corresponding to f plus g. So h tilde is less than or equal to f plus g on e. Okay? So it's f plus g minus f equals g. Okay? So this is definitely, it's a clever definition for k to force it to be less than or equal to g in this first case. In the second case, it's a little easier actually. So if this is not true, then h tilde has to be less than f of x. H tilde of x less than f of x. In this case, again, if h tilde of x is less than f of x, then the minimum is h tilde of x. So h of x is h tilde of x. So k of x is, definition again, is h tilde of x minus h of x. H of x is h tilde of x in this case. So k of x is 0, and 0 is always less than or equal to g, because g is non-negative. Okay, so in both cases, k is less than or equal to g on e. So to summarize, basically, right, we have two functions we can dump into the definition of the Lebesgue integral for respectively f and g, and to get something useful. So h and k are bounded, measurable, have finite support on e, both are non-negative. H is less than or equal to f, and k is less than or equal to g on e. Also, h tilde, remember, was k of x is h tilde minus h. So h tilde is k plus h, just trivially by definition. And because everything is bounded, everything is measurable, and everything has finite support, we know in this situation that the Lebesgue integral is additive. Okay, so right. So we use that fact, okay, and we use the fact that the integral of f over e is the supremum of all these integrals of all these h's. So it's bigger or equal to this integral for this particular h. And the Lebesgue integral of g is the supremum of all these integrals of all these k's, satisfying all this. So as the supremum is bigger or equal to this one integral. And that proves the main claim, which finishes the proof. Right. Okay. So simple consequence is the monotonicity of Lebesgue integral for non-negative f and g. And there's not a whole lot to that. Just like before, you just simply use additivity to get that, well, this is true if and only if 0 is less than or equal to this difference, which is equal to this integral here. And this is non-negative, and I've mentioned before that for non-negative functions, by definition, the Lebesgue integral is always bigger or equal to 0. Okay. And another consequence is, again, as before, that if I have two measurable subsets of E that are disjoint, then the integral of A to B, A union B of f of x, is the integral of A f of x plus the integral of B f of x. Okay. So in that regard, integrating a non-negative function behaves a lot like itself Lebesgue measure. And of course, that's critically important in probability theory. As I mentioned before, a lot of times you define probability in terms of a non-negative probability distribution function. And we'll take this a step further maybe next week, where we'll prove that integrating a non-negative function behaves exactly like Lebesgue measure, so that defining probability for a probability distribution function itself behaves exactly like Lebesgue measure does. All right, and the proof is easy. Again, integrating over A union B, the fact that that equals the integral over E times characteristic function, that's easy homework. Actually, problem 4 in exam 2 follows or implies that the characteristic function of A union B, when A and B are disjoint, is just the sum of the characteristic functions. Because there, the characteristic function of A times the characteristic function of B is always 0. You're never going to have an x in both A and B, so at least one of them is going to be 0. Again, we're assuming A is disjoint from B. Then we use the homework one more time. Sorry, we don't use the homework one more time yet. We use linearity and then do the homework one more time. All right, so that's it for the basics of the Lebesgue integral. So what we're going to do next time is prove two of the main results in the whole theory, which is Fatou's lemma and the monotone convergence. Two very important, very deep cornerstones of this entire course. And then after that, we'll define the Lebesgue integral for a general complex valued function. And we really need complex valued functions, for Fourier series, Fourier transforms, etc. For practical applications, we need to integrate complex valued functions. Okay. So yeah, we're going to next start to discuss some really deep results, in particular on interchanging integrals and limits. So before I finish off, actually, I want one more consequence. Just like before, if A is a subset of E with 0 measure, then we can excise this set of measures here from the integral, because trivially both of these are A and E take away A are measurable, disjoint. So we use just what we had above. This is 0 because A has 0 measure, so f of x, doesn't matter of what f of x looks like on E, f of x on A is f of x equals 0 almost everywhere on A, because A has 0 measure. So this integral we proved is 0, so all that's left is E take away A. Okay. Yeah, so next time we're going to prove Fatou's lemma. Okay. So long. Hopefully you did well on the exam, because if everyone did well, that means grading it is going to be a piece of cake for me. And yeah, so long. Have a good weekend. Stay safe, stay calm, and carry on. And I will see you soon.